Good morning, everyone. Welcome to the class Stability Aspects of Structural Steel Design, Concepts and Applications. We will continue our conversation on stability. In the last class, we talked about spring bar models. So previously, we illustrated the phenomena of buckling using spring bar models. We made a huge assumption that the bars are assumed to be infinitely stiff or rigid. As you can see from this one, the bars are stiff, they do not deform by themselves, as you can see from the pictures on the left. Why did we study spring bar models? Spring bar models have single or relatively few degrees of freedom so that the solution of the problems becomes a much simpler exercise using only algebraic equations. The second point is spring bar models help in illustrating the phenomena of buckling without being clouded by complex mathematics. Third, the real structures have infinite degrees of freedom, and the solution of the problems involves differential equations instead of simple algebraic equations. So in the next few slides, we will look at the governing differential equation of beam columns, which will eventually lead to the classical Euler column theory. So before we proceed further, I would like to explain the concept of beam columns. Beam column is a member that is simultaneously subjected to axial force as well as transverse loads. Consider a member subjected to an axial force P and to a distributed lateral load of intensity Q, which varies with the distance x along the member. So you can see that there is an axial force that is happening, and then there is a lateral force Q leading to the deflected shape, as you can see in the figure on the left side. The length of the member is L, and the axis are shown as it is. Consider a small element dx. The starting point of dx and the ending point of dx is AB. If you blow it up, you can see a small curve AB with a small displacement dy in the vertical direction, y direction. A moment is acting M and a shear force V is acting on the left side, and then there is a small increment in moment on the right side at point B, M plus dm by dx into dx, and the incremental shear is V plus dv by dx into dx. Now let's consider the equilibrium equation. The three equilibrium equations are sigma fx equal to 0, sigma fy equal to 0, and sigma moment equal to 0, which is taken about point B. Here in sigma fx equal to 0, P is assumed to be constant and sigma fx equal to 0 is identically satisfied. Where sigma fy equal to 0, V plus dv by dx into dx minus V plus q into dx equal to 0. Here we are taking that the load that is acting downwards, that is the positive y direction, is positive. So V plus dv by dx into dx is acting downwards, positive. V is acting on the left side is acting upwards, negative. And then the lateral force Q is acting, so Q into dx is equal to 0. So which implies Q equal to minus dv by dx. The next one is the moment acting about point B. So here we have M plus dm by dx into dx minus M minus V into dx minus P into dv plus Q dx into dx by 2. The M plus dm by dx is acting on the right side, which is in the counterclockwise direction, and the M on the left side is acting in the clockwise direction, which is negative, minus V into dx. So V is the vertical force that is acting upon a lever arm dx. So this is clockwise, so minus V into dx. And then we have P, which is the axial force acting with a lever arm of dv. So it is minus P into dv plus Q into dx is the force because it's a uniformly distributed load. So we multiply Q with dx, and the lever arm is dx by 2. So Q into dx by 2 is equal to 0. Now this M and minus M gets cancelled, and also this Q dx into dx by 2 also gets cancelled because dx is a small term, dx into dx is dx square. So we neglect the higher order terms, that also becomes 0. Now you divide everything with dx, we get dm by dx minus V minus P into dv by dx is equal to 0. This can be written as V equal to dm by dx minus P into dv by dx. So we have two equilibrium equations. One is Q equal to minus dv by dx, equation 1. V equal to dm by dx minus P into dv by dx is equation 2. So therefore, there are two independent equations with three unknowns: shear, moment, and vertical displacement. which means that they are statically indeterminate. So we need to look at the strain compatibility equation and the stress-strain relationship in order to solve this problem. So look at this curve. Basically, this is a stress-strain relationship. We are trying to understand what happens when a member is subjected to bending. So we have a centroidal axis which is in the dotted line, whose length is dx, which is green in color, and then we have a fiber under consideration whose color is given as red color. The radius of curvature is r. The d theta is the angle at which it is actually having this bent configuration, and the delta by 2 is the small displacement that we have at the bottom as well as the top. So the central axis is given as arc length is dx equal to r into d theta. So we have d theta equal to ds by r. The fiber under consideration is the arc length, which is r plus h, because there is a small h which is actually more than the radius. So radius, the fiber under consideration is acting at a distance of r plus h. So the arc length is r plus h into d theta equal to r plus h into ds by r, because d theta is given as ds by r in the previous equation. When we multiply that, we have r into ds by r plus h into ds by r. When we simplify that further, we have ds plus h by r into ds. So this ds is the original length and h by r into ds is the change in the length. The strain is given as change in length by original length, which is the definition of strain. So the change in length here is h by r into ds. The original length is ds. So when we do the same, we get strain equal to h by r. But we also know that the curvature of the beam column is P equal to 1 by r. So 1 by r can be represented as P. This means that the strain is P into h. The stress is given by strain into Young's modulus, which is again Ph into E. So now consider a small element in the cross section. It is acting at a distance, centroidal distance h. The small element is dA. The stresses will act normal to this element. So the moment is given as force into perpendicular distance. The force is given as sigma into dA. The perpendicular distance is h. So m equal to sigma h into dA. So which means that m equal to sigma is phi he in the previous equation into h into dA as per the moment equation here. So m equal to phi e into integral of h square into dA. This h square by dA is the second moment of inertia, also known as I. So m equal to phi ei. So this is the moment curvature relationship. Now let's look at the stress strain relationship. We again have a small arc whose displacement is given as d theta. The radius of curvature is r. The displacement in the vertical direction is dv. The arc length is ds. The projected length is dx. So the arc length here is ds equal to r into d theta. Divide by dx, we have r into d theta by dx equal to ds by dx. We know that tan theta equal to dv by dx, as you can see from the red color triangle shown at the bottom. So we have theta equal to tan inverse dv by dx. Differentiating this equation with respect to dx gives you d theta by dx equal to 1 by 1 plus tan square into d by dx of dv by dx, because tan inverse x is 1 by 1 plus x square. So following the chain rule, we have to again differentiate that. So here we differentiate dv by dx. So we get 1 by 1 plus tan square theta into d by dx of dv by dx. So this d theta by dx is nothing but d square v by dx square divided by 1 plus tan square theta. Substituting tan theta equal to dv by dx in this equation, we have d theta by dx equal to d square v by dx square divided by 1 plus dv by dx the whole square. Now we have r into d theta by dx equal to ds by dx. That was previously derived in the first line of the equation. Now that is equal to r into d theta by dx is given as d square v by dx square divided by 1 plus dv by dx the whole square is equal to ds by dx. By Pythagoras theorem, we know that ds square equal to dx square plus dv square, as you can see from the left hand side of the triangle, the red color triangle. So we have this ds by dx the whole square equal to 1 plus dv by dx the whole square. So basically, we are dividing this entire equation by dx. So we have ds by dx the whole square equal to 1 plus dv by dx the whole square. This gives you ds by dx equal to root of 1 plus dv by dx the whole square. So now we have this equation r into d square v by dx square divided by 1 plus dv by dx the whole square is equal to root of 1 plus dv by dx the whole square. So now r equal to 1 plus dv by dx the whole square power 3 by 2, because when we multiply 1 plus dv by dx the whole square into 1 plus dv by dx square the whole square power 0.5, you get 1 plus dv by dx the whole square power 3 by 2 divided by d square v by dx square. So we also know that phi is inverse of inverse of radius of curvature. So phi equal to 1 by r. This is given as d square v by dx square divided by 1 plus dv by dx the whole square, the whole power 3 by 2. This is the curvature of the beam column. Note, the following is derived for large deflections. For radius of curvature, we know that ds equal to r d theta. So r equal to ds by d theta. So the curvature of the beam column is phi equal to 1 by r. So phi equal to d theta by ds. For small deflection, ds is very close to dx. So we can say that d theta by ds is equal to d theta by dx. So from the geometry, slope is given as theta equal to minus dv by dx. This is from the red color triangle on the left hand side. So theta equal to dv by dx. It is negative sign is given because as we move along the x, the slope gets reduced and hence there is a negative sign introduced. So the curvature of the beam column is given as phi equal to d theta by dx, that is equal to minus d by dx of dv by dx. Simply we are substituting the value of theta in the previous equation to the value of theta in the p equation, which gives you minus d by dx of dv by dx, which is nothing but phi equal to minus d square v by dx square. Thus, we get phi equal to minus d square v by dx square, m equal to phi into ei, which gives you the equation m equal to minus ei into d square v by dx square. This is the moment curvature relationship for small deflection. Now, moment is given as m equal to phi into ei, which is m equal to minus ei into d square v by dx square. Shear is given as d equal to dm by dx minus p into dv by dx. So which means that we can substitute the value of m in the shear equation, which gives you d equal to minus d by dx of ei into d square v by dx square minus p into dv by dx. Load is given as q equal to minus dv by dx. So we substitute the value of v in the previous equation in the q. So q equal to minus d by dx of minus d by dx of ei into d square v by dx square minus p into dv by dx. So this gives you the equation. So every term has minus. So we take the minus common, minus into minus becomes plus. So the entire equation gets rid of the minus. So q equal to d square by dx square into ei into d square v by dx square plus p into d square v by dx square. So q is now given as ei into d power 4 v by dx power 4 plus p into d square v by dx square. So if you look at the left hand side, you see that the column 1 represents the condition, the next two column represents equation, the third column represents the number of equations, and the fourth column represents the number of unknowns. So we have two equilibrium equations, which is q equal to minus dv by dx and v equal to dm by dx minus p into dv by dx. The ones that are highlighted in the red color are the number of unknowns. We have two equations and three unknowns. Next, we have the stress strain relationship, m equal to phi into ei. We have one number of equations and one number of unknowns. The strain displacement is given as T equal to minus d square v by dx square. The number of equations is 1, the number of unknowns is 0. So if we add all of them, the number of equations, we have 4 number of equations and 4 number of unknowns. So there are 4 independent equations with 4 unknowns, v, m, v, and phi. The first v is the shear, the second m is the moment, the small v is the displacement in the vertical direction, and phi is the curvature. So we have q equal to ei into d power 4v by dx power 4 plus p into d square v by dx square. So for columns, the transverse load is 0. So we put q equal to 0, which means that ei into d power 4v by dx power 4 plus p into d square v by dx square is equal to 0. This is the governing differential equation for columns. Now let's look at the Euler columns. Leonhard Euler introduced the concept of buckling for long, slender columns in 1757. So, what are the assumptions of Euler columns? The column to be considered for study is an ideal column. It should be perfectly straight before loading. It's a homogeneous material and upon which load is applied through the centroid of the cross section. The material behaves in a linear elastic manner, obeys Hooke's law. Number 5, the column buckles or bends in a single plane. The ends of the member are simply supported and the deformations of the member are small such that the term y dash the whole square is negligible compared to unity in the expression of the curvature y double dash divided by 1 plus y dash the whole square the whole power 3 by 2. Hence, the curvature can be expressed as y double dash. But before we go into that, there are many people who tend to use the word Euler as Euler, but I think the perfect pronunciation for that is Euler. You need to pronounce it as O-I-L-E-R, whereas when you write it, you have to write it as E-U-L-E-R. So just a small trivia. So we look at this member which is subjected to axial compression. You can see that. So the length of the member is L. It's the prismatic cross section. Because of prismatic cross section, the I is constant. So the bending rigidity is EI. The X direction is along the length of the member and the Y direction is given down below. So when it reaches the critical load P, there is a deflected shape that you can see here. So there is a small distance at which we will take the equilibrium, that is at point A. The distance from the left hand is x. So when we look at it very closely, we have this deflected shape, deformed shape to be precise. So we had point A, the length is x from the left end, the deformation in the y direction is v. So the forces that are acting are P here, and the internal resisting moment Mi is acting as here, as shown here. So we know that M equal to minus EI into d square V by dx square, which is the moment curvature relationship for small displacement. This M here represents the internal resistance offered by the column against buckling. The internal moment Mi equal to minus EI d square V by dx square. The external moment is M sub E, which is equal to P into V. For equilibrium, taking moment about point A, we have Mi minus Me equal to 0. We know that Mi equal to minus Ei into d square V by dx square minus P into V is Me equal to 0. So we have Ei into d square V by dx square plus PV is equal to 0. The objective is to find the critical load at which the column becomes unstable. In other words, column exceeds neutral equilibrium and reaches into unstable equilibrium. Thus, substituting P critical for P, we have Ei into d square V by dx square plus P critical into V is equal to 0. This equation can be further simplified by dividing by Ei. So this gives you d square V by dx square plus P critical divided by Ei into V is equal to 0. This equation can also be represented as d square V by dx square plus alpha square V equal to 0, where alpha is given as root of P critical by Ei. The solution for the ordinary differential equation is V equal to A sin alpha x plus B cos alpha x, where A and B are constants that must be evaluated from the boundary conditions. Boundary conditions are given as 1. At x equal to 0, lateral deflection V equal to 0. Similarly, at x equal to L, the lateral deflection V is equal to 0. So when we substitute boundary condition 1, the above equation gives you 0 equal to A into 0 plus B into 1. Sin 0 is 0, therefore you put A into 0, then cos 0 equal to 1, therefore you put B into 1. So which leads the value B equal to 0. The next boundary condition at x equal to L, lateral deflection V equal to 0. So we start with 0 equal to A sin alpha L plus B cos alpha L. Instead of B, you put 0, so that becomes 0 into cos alpha L. So that becomes 0. So we have 0 equal to A sin alpha L, which means that either A has to be 0 or sin alpha L has to be 0. Here, if we put A equal to 0, it gives you the trivial solution, because if A equal to 0, B becomes 0 since already B is 0. So which means that there is no buckling that is taking place. Hence, for non-trivial solution, A should not be equal to 0, which means that sin alpha L is equal to 0. If sin alpha equal to 0, alpha L should be equal to m pi. which means that alpha equal to n pi by L. From boundary conditions alpha equal to n pi by L, we know that alpha equal to root of P critical by EI. So we put n pi by L is equal to root of P critical by EI. Squaring on both sides, we have n square pi square by L square equal to P critical by EI. The objective here is to find out the P critical. So P critical is equal to n square pi square EI by L square. So the critical load is given as n square pi square EI by L square. Here, n represents the number of half sine waves in which the column buckles. For n equal to 1, we get one single curve, which is a half sine wave. When n equal to 2, we have two curves, which is basically an S-shaped curve. When n equal to 3, we have three curves. There is a one curve at the top, which is half sine wave, and then there is another curve, half sine wave in the left side, and then there is another curve, that is half sine wave in the bottom. So basically, when n equal to 1, we get pi square EI by L square. When n equal to 2, which you have two half sine waves, we get 4 pi square by L square. When n equal to 3, we have 9 pi square EI by L square. But however, our objective here is to find out the lowest load at which it will be stable. So we take n equal to 1, which means that P critical equal to pi square EI by L square. This load is known as the Euler load. This is the smallest load at which a state of neutral equilibrium is possible. So when we look at this graph, which is vertical direction is P, which is the load, and the lateral direction, which is the x-axis, is y. So you have the lateral displacement. The point at which it buckles is also known as the bifurcation point. The load at which it buckles is P equal to pi square EI by L square. So up to the Euler load, the column must remain straight. This behavior signifies that a state of neutral equilibrium exists at the Euler load, and that Euler load therefore marks the transition from a stable to unstable equilibrium. So the one that is below this bifurcation point is the stable equilibrium. The one that is above the bifurcation point is the unstable equilibrium. So the horizontal line, the green color line, is the state of neutral equilibrium, which is between stable equilibrium and unstable equilibrium. The Euler load is sometimes referred to as the critical load. So what is a critical load? It is the load at which the neutral equilibrium is possible for a perfect member, that is idealized theoretical column. But this is not the load that will be present in IS 800. This is not the equation that will be present in IS 800. Because in IS 800, we talk about buckling load. So now what is buckling load? Buckling load is the load under which an actual imperfect column suddenly bows out laterally, which is the real column. Thus, the Euler load obtained here can be referred to as the critical load of the column, which is P critical equal to pi square EI by L square. The interesting points that should be noted are, the critical load, as you can see from above, is independent of the strength of the material Fy or Fu. So the above equation does not contain any terms such as Fy or Fu. It depends only on the cross-section dimensions of the member, which is I, the moment of inertia, and the length of the member L, and the modulus of elasticity E. As far as elastic buckling is concerned, columns made, for example, of high-strength steel offer no advantage over those made of lower-strength steel, since the modulus of elasticity for both is approximately the same. Thus, the Euler load obtained here can be referred to as the critical load of the column. P critical is pi square EI by L square. Also note that the load carrying capacity of the column will increase as the moment of inertia of the cross-section increases. Thus, efficient columns are designed so that most of the column's cross-sectional area is located as far away as possible from the principal centroidal axis of the section. This is why hollow sections such as tubes are more economical than solid sections. Furthermore, wide trunk sections and columns that are built up from channels, angles, plates, etc. are better than sections that are solid and rectangular. So, considering the rectangular cross-section shown in the figure, the buckling will occur about the AA minor axis and not BB the major axis. For the purpose of design, P critical can also be written in a more useful way by expressing I equal to AR square, which I is the moment of inertia, A is actually the area of the cross-section, and R is the radius of gyration of the cross-section. Thus, P critical equal to pi square E into AR square divided by L square. If we rearrange it, we have P by A critical is equal to pi square E divided by L by R the whole square, which gives you the factor sigma critical, which is the critical buckling stress is equal to pi square E divided by L by R the whole square. So takeaway, An ideal column is initially perfectly straight, made of homogeneous material, and the load is applied through the centroid of the cross-section. The critical load is the maximum axial load that a column can support when it is on the verge of buckling. This loading represents a case of neutral equilibrium. A pin-connected column will buckle about the principal axis of the cross-section, having the least moment of inertia, which is minor axis. The slenderness ratio is L by R, where R is the smallest radius of gyration of the cross-section. Buckling will occur about the axis where the ratio gives the greatest value. With this one, we complete this conversation on Euler buckling for pin end columns. In the next class, we'll talk about other boundary conditions. Look forward to meeting you in the next class. Thank you.